Salam alaikum. Good morning. Bom dia. Thanks for the organizer to the opportunity to present in the 60th Reliability and Maintainability Conference ISBG. My presentation today will be the reliability requirement definition based on failure mode and effect analysis and run analysis, the basis for equipment and future high performance. The outline of the presentation will start with a brief introduction about myself and my company, Eduardo Calixto Consulting. Further on, I will present the run analysis methodology, and I will clarify the methodology based on run analysis case study applied to oil and gas. Then I will conclude with the reliability requirements that comes out from the run analysis results. The second part of my presentation will be failure modes and effects methodology. Then I will present a case study applied to oil and gas, where you see the difference between design FMEA and FMEA and how to get the best from the both type of analysis. And further on, I will define qualitative reliability requirement based on failure mode and effect analysis. I will also present the concept of HALT, high accelerating life test, quantitative accelerating life test, reliability growth, and high accelerating screen test. It's all required from FMEA. And in the end, I will get some conclusions. So my name is Dr. Eduardo Calixto. I'm a CCO and founder. I'm a certified reliability professional, functional safety expert, automotive functional safety, and have some certification in artificial intelligence by IBM and Microsoft, and also master in science in R language. I have 25 years experience in different projects for oil and gas, railway, aerospace, and military industry in different organizations across the globe. ECC clients are in different industries such as railway, such as Molinari, Pros, Gematica, NRF, Ziki, RE, aerospace as AMST from Austria and Aselsan from Turkey, and also of course process such as Marshall from Dubai, Billfinger in Europe, Ocean Dream in Brazil, South America, and Siemens Energy. ECC provides reliability engineering consulting and training service, and our main focus is to support our clients to achieve high performance and keep such performance along life cycle. So we focus on three main subjects such as asset management performance, asset integrity management performance, safety engineering, and integrated logistics support for aerospace and military. In order to do that, we get support from our partners. In the Gulf region, we have United Gulf Industrial Consulting in Saudi Arabia. We have McNally in Bahrain. We have SEAC, Space Economy Academy, for training for aerospace. In Africa, we have our partner Blockstars for RAMS projects support. We have two software suppliers, HGTop Group for prognostic health management from US and HBK from Europe. And we have our partner in Asia, House in Indonesia, and Shinda in China. I suggest you to go in our website to get more information. In there you can get information about our training, about papers that you can download and see how to implement different reliability analysis, as well as our reliability database. So let's start by defining the most important concepts: reliability, robustness, and durability. Reliability is understood as a probability that a system has to operate during a specific period of time under a specific environment condition without fail. However, in addition to reliability, it is also important that the equipment has robustness. That is understood as the ability of the system to withstand to environment over stress condition without degrade the reliability in a short period of time. In addition, Durability is the ability of systems to withstand to multiple environments over stress conditions without degrading reliability. The difference between robustness and durability is that in the first case, the equipment are able to withstand to environment over stress conditions, meaning stress level over the operational limits. However, in this case, later on, the equipment will have their remaining useful life reduced. In the second case, in the durability, the equipment will withstand under overstress condition, but they will keep their remaining useful life. The very well-designed equipment in terms of performance, they have these three features: reliability, robustness, and durability. And that's the first step as an organization. We need to define proper requirements in order to our vendors to demonstrate that their equipment are reliable, robust, and durable. So let's start for our run methodology. It's a step by step. So I used to define the reliability, the run methodology, as the first step, as define the scope of analysis, and this scope needs to have all the documentation, need to be clear in order to not delay the run analysis or to do some reworks. And after that, we need to collect data, input data, reliability, maintainability input data for the run analysis. When we have historical data, yes, we perform lifetime data analysis, or when you do not have historical data for similar equipment, we need to get the information from some database. And I will demonstrate it later on here. That's we have our own database based on our previous project experience that we will provide whenever we are contracted to perform some analysis. Then the third step is to perform RBG model. I will demonstrate as well, and then based on RBG model, we perform the simulation, we get the results, we verify if the assets achieve or not the performance that's required. Then we jump for a criticality analysis that define which are the critical equipment that's more impact on the system, and then of course the final steps is to perform some sensitivity analysis. See, basically sensitivity analysis, such analysis that check the vulnerability of a system, impact of utilities, or even the design modification to include more redundant components to achieve the target. And then the conclusion. So let's go to the case study now. So this case study is about a gas offshore platform production. These are the requirements: 98 production efficiency, 98 operation availability, 9% reliability in 3 years. So in order to perform the run analysis, the first steps to get, of course, the equipment reliability data. Here we have some examples of different components, reliability, maintainability, and then whenever we do not have, in our case as a consultant company, when you get a requirement to perform this run analysis, when the client do not have historical data, we use our database. After we have this database input information for all equipment, we assess, we do what we call the assumption list for each equipment. We perform the impact of this equipment in system in case of failure, and then we build the RBG model with all the equipment listed in this analysis. Then the next step is to perform the simulation. The simulation will bring, of course, in the software, if you use, for example, RIASoft software that we mostly use, you have different results indexing there, but the most important ones are the operation availability, reliability, production efficiency that we have in this table. And then you can see that in the 4th year we starting to reduce this operation availability due to the reduction of reliability. But of course, with preventive maintenance, the idea is to bring the states as good as new, as shown in this picture on the right side. So whenever the system go to some level, I will perform preventive maintenance before the equipment fail, and then I have the equipment, restore the equipment to state as good as new. And then of course I will have this cycle that we keep the higher operation availability production efficiency by performing this preventive maintenance in a period of time. Of course, the reliability will reduce along the time, but in some time, the specific period of time that I defined, I will reestablish the reliability of the equipment and keep the system production efficiency and production and operation availability high. So another important aspect, as I mentioned, is the critical analysis that demonstrates which are the equipment that's more impact on system loss in case of failure. Here we can see that the compressor are the critical ones. So based on our RAM analysis, in the end, we need to establish which are the requirements for reliability requirement, operational reliability. Operation availability requirements. So here is an example that we have a probability density function for our compressor. So we expect that this compressor have 3.5 years of mean and half a year standard deviation. So we define as reliability 100% in 10 years. Then of course we can define beta 1 and beta 10 when we expect 10% or 1% of chance that the equipment have failure. And then of course operation availability 100% in 3 years. And yes, so we define also maintainability. What's the expected time to have to repair equipment in case of failure. And then of course here there are the maintainability requirements that we have the repair performed in less than 110 hours, and for pumps, for example, less than 32 hours, encompassing all the effects. And this requirement will assure that the system achieve the performance, the wished performance in the future. And then of course we need to also understand in this specific case that this is a field or gas field will reduce after the fifth year of production. And then of course we do not need to use all the capacity of the plant. And that was the challenge here, because if there is a high production along many years, we can just include redundancies. But even though in many cases we have to consider the plant's configuration. So let's understand how does this works. How to predict reliability when we have fuse data. So here in this template we have an example of fuse data that we collect in years. So we have our compressor failure time, and then what we're going to do is to go through the steps of lifetime data analysis. So the first step is to define which are the best probability density functions that fit in this data. So we have here different good enough fitness tests. We choose the regression in X. Then based on the regression X, the software will rank the best probability density functions that fits in this data. We choose the normal to have an easier understanding for everyone here. So let's consider that we have a mean and standard deviation as a parameter for the number PDF. How the normal PDF looks like this shape in here that we can see in the picture. So remind that depends on the data, this shape can be skewed to the left, to the right, or to the left, or it can be rounded. But in our case, a normal PDF, we have here standard of 3.5 and 0.2 as standard deviation. If you look on the reliability, we can see that the first failure takes place in 3.1 year. So we have the period of 100% of reliability until 3 years. What does it mean, and why I do not suggest to use mean time between failure? You can see that here the mean time to failure of this data will be equal to the mean of the normal PDF parameter. However, let's take another equipment that have all these 10 failures plus 2, one in 1 year, another one in 6 years. So what will be the mean time between failure? We have 10 failures that we can consider, that's 30. In average will be 3.5, but let's, to make simple our calculation, let's consider that the mean is 3. We have 30 plus 1, 31, plus 5, 36. We have 12 data, 10 plus 2, 12. Dividing this 36 to 12, mean time to failure will be 3 years. So that means if we use mean time between failure, we have this, we compare two equipment that have different performance, because this equipment that you're seeing here, they has no failure until 1 year. The second one that I'm proposing, that have one failure 1 year, another failure in 5 years, they still have mean time to failure 3 years, but they have lower performance. This equipment failed in 1 year. So let's take another example now. Consider that we have additional equipment that failure in 2 years and another failure in 4 years. So again, they have 36 divided to 12. They still have mean time to failure 3 years, but they have a failure in 2 years, early life failures. So the problem with mean time to failure, mean time between failures, that they equalize equipment that have early life failures to equipment that did not have early life failures. That's why I always suggest to use reliability and beta parameter. But what is beta? Beta 1% or beta 10%. Beta 1% is the time that you have a chance to equipment have 1% of chance of failure. So that means in 2.8 years, 1%, they have 1% of chance of failure. So in other words, if we have here, we have beta 10, that we can apply different types of beta. Here the chance of failure is 10%. What's the time that they have 10% of chance to have a failure? 3.117 years. So what does it mean in practice? If I have 10 compressors, one will fail in 3.117 years. And that gives me a very clear picture about early life failures, when the early life failures take place. That's why, in addition to reliability, this beta 1% or 10% is very good index. However, during operation, we also need to verify and validate the equipment reliability performance. But in many cases, during operation, because the operators do not have time or skills to perform this type of statistical analysis, the ideal situation is our enterprise asset management solution. They have embedded a FRACA system. Then, whenever that some failures take place, the operator or technician or engineer will input the failure data in the FRACAS. The FRACAS is online. They already have some classification of a failure modes for cause, for description. That is very fast. And as soon as they start to do that, the FRACAS will be connect what we call reliability 4.0. So as long as we have at least 3 failures, here we have 4, we can define the viable parameters beta and eta, and based on it we can define the reliability in a specific period of time. All we need to do is to define the time that we want to target and click to calculate. The solution here will calculate automatically the beta, the eta, the reliability. In addition, they calculate mean time to repair, and they calculate different 2 other parameters here: failure intensity and mean time to failure. This mean time to failure is mean time to failure instantaneous, means this mean time to failure in this specific period of time that we define here, because that's use the growth answer methodology, the reliability growth analysis. So in the first case, we can also see graphically that we have in red our targets and in blue what we want to achieve in terms of reliability. And we can see very clear that the equipment is under their performance. And all we can see also in terms of probability of failure, that is higher than we expect. That's very important for safe equipment. Or we can see also the profile of failure rates. In the same aspect, we can also see the failure intensity graph, the mean time between failure, and that is very useful, mean time between failure, because here we can see that mean time between failure are decreasing a long time. And that's very important for maintenance engineer, for a maintenance technician, that they are able to check how fast their equipment are degrading, the interval between failure are increasing or decreasing. And then we can also have the expect time to failure. That's also calculate the first template. Need to keep in mind that's the issue that we have in reliability is that we calculate such index after the failures take place. These are very important index to compare and different vendors equipment performance to validate, verify if equipment achieving their reliability targets. However, during operation we need to monitoring our remaining useful life of our equipment state of health, and that we are going to do by using prognostic of management. So in here, one of the functions embedded in the enterprise asset management is based on online monitoring. Here, temperature, I can predict the remaining useful life, the end of life, and state of health of equipment, and that's will enable me to plan some preventive maintenance interventions. So let's take a look on how we proceed to define these requirements in practice. So let's go a little bit deeper when you perform lifetime data analysis. So basically, we collect from our historical data the time that's a specific equipment failed. So here we consider a compressor and can be a specific component, of course. So we have here basically we use the Viable software to perform this analysis, and here we have different goodness of fits tests. We use a regression in X, and then by using regression X, the software will basically define which are the best probability density functions that fits in our data. Here to make simple the understanding of our presentation, we define the normal PDF. So here we can see we have a mean as a 3.5 years, standard deviation 0.2. So and that's very important point when you discussion about mean time between failures. So here we can see the shape of probability density function is normal distribution with standard deviation 3.5 with 0.2, and basically we see that after this specific period of time, if you plot here, the failure rate also starts to increase. And here automatically in the software we can also plot the reliability, and here are the points the failure, and we can see that the first failures happen in 3.1, and before this time we have 100% reliability, and that's why I do not recommend to use mean time to failure, mean time between failures. So why? So for example, let's consider this sample of data here that we have, and then let's now consider that we have one failure that's happened in 1 year, and the other failure will happen in 5 years. So in the end of the day, we have 10 around 10 times around the 3, that will be around 30 plus 131 plus 5 36. So 36 divided for 12 failures, this 10 plus 1 plus another one here, that's 5 years. So around here 5 years we have 12. So 36 divided for 12, we get 3 years. Mean time to failure will be 3 years, very similar that we have in normal distribution. However, in this specific case that we're discussing here, we have one failure that takes place in one year, and then if we use the mean time between failure, we are assessing the same performance of equipment that did not fail during these 3 years, comparing with equipment that had already 1 year failed, and then we say this equipment have the same performance. That can happen when we use mean time between failures. So again, if you can have one failure in 1 year, another failure in 2 years, and one failure in 5 years, and another failure in 4 years, 4 or 5 years. So we have 1, 2, all these failures, and we have 4 and 5. So basically, we have 30. We have 1 plus 2, 3, and 3 plus 4, and we have here 4. So we have 1 plus 1 plus 2, 1 plus 2, let's put 2, 1 plus 2, 3, and 3, and we have 5 and 4. So we have here 12. So we have here 42, divided for, we have 10, we have 14 days, and then in the end the average will be 3 years as well. So in the same, another example that we have here, one failure, two failures occurring in 1 year, 2 years, and then if I use mean time to failure, they will compare one equipment that have failures in 1 year, in 2 years, they will show that they have the same mean time to failure when we compare with equipment that have no failure. So that's why I do never recommend to use mean time to failure. So another aspect that we are discussing that was not present in the requirement, but I would like to present it now to have a clear definition, is the beta. Beta 1% means which time we have 1% of chance to have one failure is 2.8 years. And here we also calculate 10% of failure, so that means 3.1 years. So that means for this 10 failures. So this is how we are defining the quantitative target, but we also need to define qualitative requirements. So basically the failure FMEA methodology, we define the equipment, we perform the FMEA, then we define recommendations, tasks, and follow up the application. So in order to perform the FMEA, we need to have a risk matrix that's combine probability and effects, and here we have some definition of which are how is classified the effect. So we have two examples here, the usual examples that is carried out when we perform FMEA for in oil and gas for plants. So here you can see that we have, for example, a shaft, so we can have two failure modes, worn out, fracture, and that's cause is for example, case of fracture is a high vibration. Then of course most of cases we define we implement RCM to define how I will detect this high vibration by online monitoring, and then there's the usual failure mode and effect analysis. Why I demonstrate in the second FMEA template is that I also consider not only the cause but root causes. So if I look on the same fracture example, for example, I have loss of robustness to high vibration, and yeah, this is the cause. The root causes high vibration. Then as a requirement, I define a reliability test to assure that this shaft can sustain in a higher vibration, higher than specified, and then I apply that for all equipment. So what we're going to do if we do not have a FMEA? FMEA involve a lot of resource and time. So again, when we are involved in this type of projects, mostly we use our database as startup to speed up and get a faster FMEA and implement faster recommendation. So as a result of FMEA, we have some qualitative reliability requirements. For example, if we have a control, we can check here this example to implement vibration tests concerning different types of tests: high accelerating life test, quantitative accelerating life test, RGA. So what does really means high accelerating life test? So basically I have different types of machines that will test such equipment. So here I have a chamber for temperature. Here I have equipment that we test vibration and shock. This one I shock, and this one I can test winds, for example. This one I can test the vacuum, resistance of equipment against vacuum, and here I can test, for example, vibration and temperature. So the whole idea is that for the HALT, if I have, for example, equipment limits temperature in 50 degrees Celsius, so are you starting to increase this limit here or decreasing with minus 10, are you decreasing for minus 20 until the equipment failure? Then when the equipment failed, are you find out the equipment weakness, the material or something, assembling, design issues, and I will fix that, and then I will extend the upper limits of operation. Now the equipment is more robust because they have a higher level of, they resist an over level of stress. So that's the HALT idea. Then I go to my second step, is quantitative accelerating test. The main objective here is basically to have minimal numbers of samples of prototypes, the same equipment or components. Then I will do a higher level of accelerating tests. So if in my case of my temperature, that's I work on 60, 70, now I go 75, 80, and then the equipment will fail. Then I get these 5 prototypes, check the equipment fail in a specific period of time. Based on this time, that will be in some days or weeks, I can apply accelerating factors that will translate how long these failures will take place in a normal condition. In other words, I can predict the reliability in usual condition by accelerating them. If they not achieve the targets, I will need to improve, make some actions, and test again. And whenever I make some improvement, test again, and check the period of time, that is what we call reliability growth analysis. Basically, I will checking and make some implementation, some increasing of reliability, and my mean time between failure signs increase. So that's very good for design, but I need to be careful with assembly and production. After assembly, I will apply what we call HASS, High Accelerated Screening Test. And this level of stress here is the same concept of stress. For example, temperature, I put my equipment in the chamber, and then, but this level will be lower than HALT and higher than operation specification and defined. So if I did the HALT in 70, I will probably put it here in 60. My objective is to get failures, screening failures that was triggered during assembly or manufacturing. Then I fix that, I adjust my manufacturing, my assembly, and avoid this failure. So as conclusion, in the very beginning, I need to define my reliability requirements that will enable my system achieve high performance. That is part of requirements definition my bid process to select my vendors. My vendors, we need to apply different reliability methods, lifetime data analysis, run analysis, even test, to give assurance of their equipment reliability. And then we will be able to achieve high performance during operational phase. So as the last message, I would say that the best maintenance and AI strategy is to have reliable and robust and durable equipment. So the reference for this presentation is my book, Gas and Oil Reliability, where you can find these run analysis case studies and different chapters about FMEA, RCM, lifetime data analysis, even risk analysis, human reliability analysis, and asset management. And my new book, Artificial Intelligence for Maintenance 4.0, Manual for Maintenance Engineer. Basically, in this book, you will find one chapter that describes the whole concept behind prognostic management, as well as different chapters that describe the main concept about machine learning, supervised machine learning classification prediction, and unsupervised machine learning to cluster and optimize maintenance. In addition, you can also find different topics in this book, such as reinforcement learning for optimization, maintenance tasks, and natural language process. In the end, you see a chapter about asset management. Thanks for your time. I'm open for your questions.